Hello, and thanks for using TickBoom. In this video, I'm looking at the 2000 Advanced Math HSC question 10 being the final question, or 10B here. The reason I'm looking at this is I've been doing a little bit of a series where I work through all of the final questions of the HSC math exams that I sat. So I did my HSC back in 2001, but at the school I went to, if you wanted to study 3-unit math or extension 1 math, you had to first do the 2-unit exam in year 11. So you had to do it a year early. I'm not sure whether our school was unique in that. I'm sure there's plenty of other schools who take the same approach. I think it makes sense because you kind of knock out the exam in year 11, and that way you don't have to worry about it when you're in year 12. I think our school also used it as a bit of a way to sort out those students who really should or shouldn't be doing 3-unit. So I think the idea was if you wanted to give 3-unit a crack, sit the 2-unit exam in year 11. If you do well, then they'll let you do 3-unit. If you don't do well, then maybe stick with 2-unit and give it another try in year 12 and kind of pick the higher of your 2 marks, I think is what you could have done. So my plan was always to do 3-unit, just 3-unit. So naturally I sat this exam. In the end, I ended up doing better than I thought I would. I think my mark was 93, which on the face of it doesn't sound particularly good. Probably I was happy with it, getting in that kind of top band. But the thing that really surprised me is that mark of 93 actually got me on the merit list. I actually ended up keeping the newspaper, which I've got here from all those years ago. That the Daily Telegraph in this case was the one that kind of listed all the students, and actually when I flick through, there's a whole bunch of articles here about HSC and life after the HSC. I think the newspapers still do this, but then they kind of went through and for every subject listed out. I'm not sure how they decided who to list, but I guess the top performing students in various subjects. And here we are for mathematics, 2-unit math. I kind of found my name in the newspaper over here, down here, Nathan, Marston College Randwick, 47th. And I thought, wow, okay, top 50 rank. Interesting. I mean, I'd always done pretty well at math at my school, but I never really thought that I was particularly good at math. I mean, I don't think I am particularly good at math. I have the ability to, I guess, study and eventually work stuff out, but math doesn't come naturally to me. It's not like I have this innate ability to just know the answers like some people seem to. But actually getting that ranking is what gave me the confidence to say, hey, maybe I should give 4-unit a try. Maybe I'm not good just in the context of my school. Maybe I should try the most difficult math that you can at high school. And so in the end, my performance in this exam didn't matter because I ended up doing 4-unit, which means your 2-unit mark doesn't get counted. But I'm very glad I did 4-unit because it ended up being definitely my favorite subject at high school. I personally think it was the only subject I did in the HSC that somewhat prepared me for what learning at university would be like. In my actuarial studies degree, I found that whilst the lecturers and the teachers may have been very good actuaries, they were not very good teachers at all. I don't think they were interested in teaching. I don't think they were good at teaching. All that degree really was one test after another. They were just testing us to see who could perform the best. And fundamentally, from my perspective, that degree was just them telling us what we had to go and work out ourselves. And I feel like 4-unit math had that element to it, where it was the one subject I did where some of the content, some of the questions were beyond the teachers that I had. You know, you go to a teacher and say, how do you work this out? And every now and then you get an answer of, I don't know. And you really had to do that independent learning. It was the only subject where you had to go and work stuff out yourself. And if you didn't have that initiative and persistence, then it would be very hard to do well. And I think doing that in the HSC really did prepare me for the actuarial studies program to come, because that's basically what that whole program was like, just working stuff out yourself. So yeah, that's that. I mean, this particular question, this question 10B of the 2000 exam, if you were to say go and Google, you know, what's the hardest 2-unit HSC question ever, this question pops up, surprisingly. I don't think it is necessarily that hard, but it certainly is regarded as one of the hardest 2-unit math questions that have kind of come and gone. I think it's mainly because of the way it's worded as opposed to the actual math required. I would say reworking through it now, the wording is fairly confusing. Even, you could argue, potentially ambiguous, but I think that's why a lot of students historically have struggled with this, because you're just dumped with a whole bunch of information, and you know, that can be daunting for some people. So the way the question reads is, it says, the first snow of the season begins to fall during the night. The depth of the snow H increases at a constant rate through the night and the following day. At 6 a.m, a snow plough begins to clear the road of snow. The speed, v kilometers per hour, of the snow plough is inversely proportional to the depth of the snow, which means that v is equal to a on h, where a is some constant. We're told to let x kilometers be the distance the snow plough has cleared, and let t be the time in hours from the beginning of the snowfall, and let little t equal big T correspond to 6 a.m. And I think that little bit there is potentially confusing, and we'll see why later. Part 1 says, explain carefully why for little t greater than or equal to big T, dx dt equals k on t, where k is a constant. And then part 2 says, in the period from 6 a.m. to 8 a.m, the snow plough clears 1 kilometre of road, but it takes a further 3.5 hours to clear the next kilometre. At what time did it begin snowing? End of paper. And you can imagine, you know, all the students who've kind of grinded through the exam, they get to this final question, and then this gets dumped on you. You can see why a lot of people might have just hit a wall at this point. They're probably already fatigued, and whilst we'll see that the math isn't particularly complicated for this question, it's deciphering all this information that makes it hard. Alright, so I might just move this, and if we start with part 1, what we're asked is to explain why dx dt is equal to k on t for little t greater than or equal to big T, where this big T corresponds to 6 a.m. So basically, when it's after 6 a.m, explain why dx dt is equal to k on t. Now, I think from all that information we were given in the question, for this part, the key thing to draw out is that h, the height of the snow, is directly proportional to the time that has passed since it started snowing. And if that's the case, then what we can do is we can let h equal to some constant, I'll just call it c for constant, times t, where c is a constant. So that's the classic way that you can reflect mathematically when two parameters are directly proportional. So from there, we're concerned with dx dt, and we know that by definition v is equal to dx dt. That is the definition of v. And we also know, we're told, that v is equal to a on h. So if both of these things are equal to v, we can just equate them. So therefore, we can say that dx dt is equal to a on h. And as we've just noted, h is equal to c times t, where c is some constant. And I can write that as A on C times 1 on T. And I think this is where maybe not all students would think to do this, but I can then write that as K on T, where K is the constant A on C, i.e. constant. I mean, when you're dealing with constants, it doesn't matter what you call them. So if I have one constant divided by another constant, that is just some other constant that I can call K if I want to. And I think some students might find this a bit confusing. Maybe they think it's like a bit of a trick and you shouldn't be allowed to do that. But constants are constants. Like, 10 divided by 2 just gives you 5. And 5 is just another constant. So I think the key to this part, that is part 1 done. So not particularly difficult. But I suspect a lot of students might not have got the marks for it because maybe they didn't kind of make this leap here based on the information provided, or maybe they didn't kind of realize that you can take one constant and just call it something else if you want. But that is part 1 done. So now part 2 asks us fundamentally, when did it start snowing? And we're given a bit of information to help with that. So when did it start snowing if, and the first bit of information we're told is that between little t equals big T, or in other words 6 a.m, and 8 a.m, which corresponds to little t equals big T plus 2 hours later, x is equal to 1 kilometre. In other words, we ploughed through 1 kilometre of snow. So that's the first bit of information we can use. The second bit, we can say that between t is equal to big T and t is equal to big T plus 5.5, x is equal to 2 kilometres. And that wasn't given to us directly, but what we were told is that it takes another 3.5 hours, so 2 plus 3.5 is where you get your 5.5. Takes another 3.5 hours to go 1 more kilometre, so from 1 kilometre to 2. So you kind of had to deduce that, but now you can kind of guess, I hope, that with these 2 pieces of information we can probably come up with 2 equations, do some simultaneous equations, find out t. So find out how many hours had it been snowing at this 6 a.m. point, and then work backwards that many hours from 6 a.m. That must be when it started snowing. So let's work through that. I mean, fundamentally, x, the distance, is the integral of v dt. That's the definition. If you want to go from x to v, you differentiate it. If you want to go from v back to x, you integrate it. So therefore, we can start by saying that the integral between t and t plus 2 of v, which we've just said can be written as k on t, dt, that's going to be equal to 1, the 1 kilometre. And I might just turn over to start evaluating this, but in terms of evaluating that integral, we can bring the k out, because that's just a constant. And then what we're left with is the integral of 1 on t, which hopefully, you would have had to have learned that that's the natural logarithm of t between t and t plus 2. So we know that's equal to 1. So if I evaluate that, we'll get k natural logarithm of t plus 2 minus natural logarithm of t equals 1. And by the rules of logarithms, I can just write that as k natural logarithm of t plus 2 on t equals 1. And that's because the log of a on b is equal to the log of a minus the log of b. So you can then work in reverse to write it in this format. And I might call that equation 1. Now we're going to do basically the same thing, but we'll use the second piece of information here. So we'll say that the integral from t to t plus 5.5 of k on t dt is equal to 2. And we'll do the same thing to integrate, bring out the k. The integral of 1 on t is log of t between t and t plus 5.5, that's equal to 2. So we'll get k log of t plus 5.5 minus log of t equals 2. I can bring those together, t plus 5.5 on t equals 2. And that I'll call equation 2. And we're pretty close to being able to do some simultaneous equations. One thing to help make this simple is that this equation 1, the right-hand side has a value of 1. This equation 2, the right-hand side value has a value of 2. Now, wouldn't it be nice if they both had the same value, because then I could just set them equal. So that's what I'll do. I'll take equation 1 and I'll multiply it by 2. Multiply both sides by 2 so that you haven't changed anything. So we'll get 2k log t plus 2 on t equals 2. And I'll call that equation 3. Now, because equation 2 and 3 have the same right-hand side, it means the left-hand side must also be the same. So I'm going to equate equation 2 and equation 3. So what I can conclude is that k log t plus 5.5 on t is equal to 2k log t plus 2 on t. The first thing I can do is cancel out the k's. The next thing I can do is use the rule that log of x to the y is equal to y log x. So I can use that in reverse to bring this 2 up. So we'll get log t plus 5.5 on t is equal to log t plus 2 on t squared. And now I can say, well, if I've taken this function, the natural logarithm of both sides, and if they're both equal, then it means the thing I'm taking the log of must be equal. And I might turn over to continue, but so what we can say is that t plus 5.5 on t is equal to this side, and I'll just write, I'll expand the square into the top and bottom, so we'll get t plus 2 squared on t squared. Alright, I think I can multiply both sides by t to cancel that t and cancel the square. And then if I bring the t up, we'll get t squared plus 5.5t is equal to the first one squared plus twice the product plus the last one squared. Now we've got a t squared on both sides, so they can go. I might bring the 4t over, so I'll get 1.5t is equal to 4. So t is equal to 4 divided by 1.5, or if I just double top and bottom, that'll give me 8 on 3 hours. Which, if I get my calculator out, if I do 8 divided by 3, that's going to be 2 hours. And I'll just subtract the 2 to see what's left. So it's that fraction of an hour. So if I times by 60, that'll give me the 40 minutes. So at capital T, the snow has been falling for 2 hours and 40 minutes. And I think this is where the question is quite confusing, because we're told, you may remember, that T is equal to T corresponds to 6 a.m. And I can see a lot of students going, well, if T is equal to T corresponds to 6 a.m., then isn't capital T 6? How can T be 8 on 3? It's meant to be 6. Like, what's going on? Like, I can imagine that confusion. But actually, what the question writers are really trying to say, and I think this is up for debate whether it's ambiguous or not, is they're saying that at a certain value of T, capital T, whatever value that takes, in this case 2 hours and 40 minutes, that's what little t is. So little t equals capital T means the snow has been falling for little t hours, 2 hours and 40 minutes, at this capital T, which happens to correspond to 6 a.m. So what you conclude is that at 6 a.m., therefore at 6 a.m., it has been snowing for t's equal to 2 hours 40 minutes. Therefore, the snow started at, and then you just have to work back 2 hours and 40 minutes from 6 a.m. So you say, kind of, you know, you may make a mistake here, but you just want to check. But if you said 3:20 a.m., you can see that 3:20 a.m. plus 2 hours is 5:20, plus another 40 minutes gets you to 6. So the snow started at 3:20 a.m. and that's the end of the question. So that is how you would tackle what is considered by some to be the hardest 2-unit question that there's ever been, which I don't agree with. I think there's probably been harder questions probably after this one, but perhaps at the time this was considered by many to be the hardest 2-unit question that the Board of Studies had thrown at anybody. But as we see, you know, as long as you understand constants and basic integration, you know, you get there. And I think it all comes down to the way the question was worded. Very confusing. They probably could have found a better way to, I guess, lay out what all this meant. But I think there would have been plenty of students who got this, who worked it out. I don't think I was one of them. I may have got a few marks, but I doubt I got all of this, given the state of my math at that time. But yeah, I actually did look up the Board of Studies notes, where they kind of write notes on how students did, and they did say that the vast majority of students got 0 for this, for the whole question. They got no marks. They kind of pointed out some students picked up a mark in part 1, but very few students got part 2. And I think they shouldn't be surprised by that, because the wording of it was not helpful. So no doubt they've learned a lesson from that, and they've probably tried to improve. You would think that when these people write their questions that they put it through testing and they try it out on students to see. I'm not sure. But yeah, anyway, hopefully you found this helpful, and that if you were going back as far as 2000 for your practice, that you know, if you came across this question now, you'd be able to give it a good crack. I know they've changed the syllabus a few times since the year 2000, so I think it's not uncommon that students don't bother going that far back, but I think the changes to the syllabus weren't so great as to mean questions like this are now irrelevant. I think a question like this is worth knowing how to do, and so there is some value, I think, in going back to these older HSC questions, and yeah, it may take a bit of effort to kind of work out which questions are still relevant in the curriculum and which aren't, but I think there is some value in these older questions, and it's not a bad thing to go and take a look at them. So hopefully you found all that helpful and insightful, and tick boom.